For anyone who doesn't know me, my name's Adam Trumper, and I'd just like to welcome everybody to this kickoff for our Launch Canada lecture series. So with the pretty massive surge of interest in rocketry here in Canada, Launch Canada is all about helping the students to harness that enthusiasm and really run with it as far as they can go. So while the COVID-19 situation has meant that rocket competitions and a lot of the hands-on activities are on hold, we're starting this virtual lecture series to make sure that the students can continue learning how to be successful at advanced rocket development, how to approach these activities safely, and hopefully find some inspiration along the way. And I think it's hard to imagine a more inspiring speaker than Peter Beck, the founder and CEO of Rocket Lab, not only because he managed to do what few people have ever done and build a successful launch vehicle company, but he did that starting as, for lack of a better term, an amateur, and not in Southern California, but in New Zealand, which was not known for its space launch expertise. So for all of us here in Canada, I think that's a struggle that we can definitely relate to. And we are incredibly honored to have Peter as the first speaker in this series. So this is going to be a fireside chat. I've got some pre-prepared questions that I've put together to frame some of the discussion. And we will be taking as many questions from the students as we can. So before I turn it over to Peter, I'm just going to very briefly unmute everyone, and let's get a very warm Canadian welcome for Mr. Peter Beck.
Hello, Peter.
Hello.
Hello. Hey, Peter.
Hello. Hello.
Hello.
Hello.
Hello.
Hello. Hello, Peter.
Hey. All right.
Oh God, why? Why are we doing?
All right. So Peter, I think that we've got several hundred students here from all across Canada who are definitely all ears to hear what you have to say. So, would you like to maybe give the students just a very quick introduction to Rocket Lab? I think everybody generally knows who you guys are, but tell us what you're up to.
Yeah, sure, and thanks for the warm welcome. That was the weirdest Zoom meeting I think I've ever started. So thanks very much for that. For those of you aren't aware of Rocket Lab, so we're I guess we started off as a small launch company. But more recently, I guess I'm reassessing whether we should have called it Rocket Lab, because we do much more than rockets these days. So obviously, most people will be familiar with the Electron launch vehicle. We've just started building satellites, the Photon satellite platform, which we can talk about later in more detail. But it's basically a multifunctional bus. And then we also do ground operations and end-to-end services where customers come to us and they say, "Hey, we want to do this," and we go, "Okay." We build the spacecraft, we put it in orbit, and we manage it for them. The company it was started in New Zealand, so I started in New Zealand in 2007. But now the company is headquartered in Long Beach, California, and we have operations, large operations in New Zealand. So majority of R&D is still done in New Zealand. The majority of the workforce is in New Zealand, but we have operations in obviously Long Beach, where we do all propulsion and avionics, and then we have LC2, which is a launch pad in Virginia, as well as a processing facility, and then in Australia we have some people, and we just recently acquired Sinclair Interplanetary, which is a Canadian company. So we officially have rocketlab.ca now. So we're all over the show, a little bit like the coronavirus, really. We're everywhere. But generally, all of our activities boil down to one kind of fundamental thing. And if you ever come to any of the factories, you'll walk in the door and the first thing you'll read is that we go to space to improve life on Earth. And most space companies have a clear mandate about what they want to do. Some want to go to Mars, some want to mine asteroids, some want to do other things. My view has always been that if we can build really powerful infrastructure in orbit, we can have massive influence in a positive way to everybody's life on Earth. So that's what wakes me up in the morning. That's what gets me motivated. I love building infrastructure in space and seeing the consequences of doing that in a positive way. So everything that we do basically boils down, to that main objective.
All right. So Peter, I think one of the really impressive things about what you did in building Rocket Lab is you were able to do it, or at least a lot of it, in New Zealand, as you mentioned, and you didn't start as a veteran of that industry, but as more of an amateur grassroots rocketeer. So could you tell us a bit more about just how you managed to do that, and whether maybe there are any lessons from your own experience that you could share with those of us here who would aspire to do something similar?
Yes, don't do it. Don't. No. Yeah. So, I mean, look, there's really only two things that have ever been of interest in my life, and that has been engineering and space. And I started building rockets when I was at school, mainly rocket engines, actually. So that's where I started. I quickly found the internal combustion engine insufficient for the things that I wanted to do. The energy density was way too low. So I started building rockets, and everything has always been about the rocket. So even though I started as an apprentice tool and die maker, I would run the day shift doing my job, and then the night shift I'd be working on rocket bikes and rocket packs and rocket scooters and all those other kinds of things. And generally the way it would go is I would build an engine, and then I would figure out what I could put it on. And I think it's true testament to your engineering confidence to put a leg either side of your rocket. That's when you've got to get it right. And for me, it was, I know there's a lot of shortcuts that get taken, especially in the early stages of rocketry. But I think one of the key successes was, I never built anything unless I had a really good understanding of the physics, the engineering behind it, and the the hazards and the dangers. So I remember, the very first rocket I built was a hydrogen peroxide monopropellant. And I could only source the hydrogen peroxide at 50% concentration. So I had to build a bubble reactor column to get it out to 92 for it to be useful. So, I put a garden shed out the back of my property, dressed myself in fireproof suits and rubbish bags and welding helmets, and set to build a bubble reactor column. But I know that sounds kind of dodgy and kind of mischievous, but it was well researched, and I never felt like I took any great risks. However, I did have one incident with it. I brewed a really good batch, and I actually got a little bit of a chemical burn on my finger, and in the haste of it all, I tipped it down the sink with running water, and melted all of the piping in my house. So there was water spraying everywhere out of every leak trap from there onwards. So, but anyway, in terms of PVC, cement is soluble with high concentrations of hydrogen peroxide. But all of that was always, that's kind of where I started. And right throughout my career, even though, I went and once I finished my apprenticeship, I moved into the design office, and I was, design and analysis. It was always the same, the same approach. Day job was really fueling my information and engineering experience to do my night job. And that went right throughout my career until finally I ended up at a government research laboratory, and mainly researching advanced composites and materials, and superconductors. But all the time, I was leveraging the government's assets at night to build my rockets. And things just got things got bigger and bigger and more complicated until finally I felt like I'd reached the point that I could do something with it, and went on somewhat of a rocket pilgrimage. So I went to the US for a month, and I went around and visited all of the places that I could, some that I couldn't, and I visited Mojave Desert, spent a bit of time out there, and saw what all the guys in the little shops were doing. I got chased out of the Edwards Air Force Base. That was a little bit embarrassing. But ironically, I was invited back by the base's commander a number of years ago, and I enjoyed driving through that gate, the same gate that I got hushed out with a man and a gun. But anyway, so it was it was really, really important to make that trip, because I learned a couple of things. The first thing I learned was that what I was doing back at home was not far away. In fact, it was pretty much identical to what all the little companies in the Mojave Desert were doing. They were having, the same issues with injectors and the same issues with combustion, and they're using the same National Instruments equipment that I was using. So there was not like this massive level from where I was operating, which came as quite a big surprise. And then the other thing I learned was that with respect to small launch, nobody was doing anything that was of super exciting at the time. So, and everybody I spoke to, just sort of said, well, maybe that will happen one day, or until the government tells us that that's what they want us to do, then we'll just leave it at that. So I returned home, and on the flight home is where I decided that I was going to start Rocket Lab and go after it myself. So it's kind of like 13 years in a few minutes.
Wow, that's impressive, and I can definitely sort of sympathize with some of your experiments at home. Although I admit I haven't disintegrated my plumbing with hydrogen peroxide yet, so that I think is a valuable cautionary tale for everybody. So
that one's still a mystery. Because PVC shouldn't have really bothered it, but anyway.
Well, hindsight is 20/20. Good to know for the future. So when you started out doing this in a country where launch vehicle development was very much outside the norm, what were some of the big obstacles that you faced? Were there any that really stand out? And if so, how did you overcome those?
The first thing to do is listen to nobody, because you're right. New Zealand had no space industry at all, and I remember when I'd started the company, I was trying to get some government grants, and for me it was very, very sound engineering, very sound business plan, and a very clearly laid out path about how we were going to do what we were going to do. And the government agencies at the time, just because it had the word space in it, just thought it was the most insane thing at all. And I remember escalating it right up to basically the chief executive of the grants department. And we had a meeting over lunch, and he said, the problem you're going to have, Pete, is that New Zealand will never do space. And when those words came out of his mouth, that was probably the time that I decided, well, I will die trying, because you're wrong. And this has been consistent throughout my life. I mean, my careers advisors at high school called my parents in because I told them that I was going to build a rocket company and I was going to go to space. And I said that my aspirations were unrealistic, and I needed to, I was good with my hands, and I should go down to the local aluminium smelter and get an apprenticeship as a fitter turner. So the thing is that there's some things in life where no is just the wrong answer, and that was one of them. So yeah, I think there's no like singular kind of struggle. I mean, it's just a continual slog, even today. I mean, once we started, there was always a lot of skepticism, and it was always perceived as this crazy guy who he previously worked at a government lab, and he wasn't dumb, but clearly something had happened to him as a child. So it was a lot of skepticism, and it wasn't really until I went over to Silicon Valley and raised the first chunk of capital out of a tier 1 firm, where a few people sort of looked sideways and said, "Oh, what was a tier 1 VC firm in Silicon Valley pouring money into a New Zealand enterprise for this, especially a rocket one? This doesn't make a whole lot of sense." So as that kind of grew, and as you understand how governments work a little bit more, we're able to turn the tide on that. But I would say the majority of New Zealanders still think of us as a bit of a curiosity, rather than the only small launch vehicle flying in the world. It's more, I have a lot of New Zealanders ask, when my sponsorship's going to run out for launching these rockets, and they have no concept that we're even putting satellites into orbit or what the whole point of it. They think it's
Right.
just it's just a couple of guys down in a paddock somewhere shooting off some rockets, and not a billion-dollar corporation with 500 people working flat out. So there's and we have a lot of issues with education within New Zealand. Actually educating people. It's ironic, really, because a small island nation in the middle of nowhere is completely reliant on space, absolutely completely reliant, and in your everyday lives. But yet, very, very few people have an understanding of that. So we do a lot in schools, a lot of education programs to try and change that. But launching out of New Zealand was no easy feat. Excuse me. In order for us to launch out of New Zealand, we had to attain a bilateral treaty between the United States and New Zealand, because New Zealand didn't have a space launch capability, so it was in violation of all of the MTCR treaties. Yep. So we had to get a bilateral treaty between the US and New Zealand, and then once that bilateral treaty was signed, there's a whole lot of rules and regulations that had to accompany that treaty. So we had to put through Parliament, through Select Committee, and then ultimately into law a whole lot of new rules and regulations. Then those rules and regulations needed a regulator, so the New Zealand Space Agency was created. Then the Aussies got jealous, and then the Aussies created a space agency. So there's, I would say that regulatory is a third of Rocket Lab's business. Third of the amount of stress, third of the amount of work. It's just huge amount. And then a third of it is infrastructure. So I laugh hilariously loud whenever I see companies that propose to build launch sites as a business, because that's got to be the dumbest business on this planet. Somebody who think they can build a launch site and for any old rocket and make it profitable is crazy. But nevertheless, we had to build launch sites. We had 32 kilometers of road. We had to upgrade internet backhauls to entire townships. We put tracking dishes all around the planet. So we've got tracking dishes and 5.5 meters on the Chatham Islands, Cork, Azores, Southland, Australia. The infrastructure is just huge. So I don't know really that answers your question, but there's not one kind of singular challenge. It's just waves of challenges.
I mean, the piece you mentioned about the government, I think, is something that's certainly very relatable here as well, because if you're in a country that doesn't have any previous infrastructure or regulatory framework for these things, it's no longer enough to just build a rocket or even build a rocket and a launch site. You also have to build the necessary treaties and regulatory regime to support it. And obviously, to be able to do that requires a certain amount of buy-in from the government. Yeah. So how did you approach that in New Zealand? How did you convince them that this was actually worth their while to get behind?
Yeah, so I mean, there's a number of things there. So firstly, having critical mass. So the New Zealand government had to take stand up and listen when, the company was really well funded by some of the best in the industry, and there was a lot of push from the US government as well. So, when the ambassador has to turn up at the State Department for a meeting, then that starts to get on people's radar a bit more. And, like I say, sometimes no is the wrong answer. So never be afraid if it's really important. No is just yes on a different day with a different set of circumstances and leverage. So that that's not always the acceptable answer. And we were also very lucky to have a government at the time who believed in what we were doing. They saw the opportunity for the country, and we were very lucky to have a minister by the name of Stephen Joyce, who was basically the minister of everything, one down from the Prime Minister, who said, let's make this happen. And every government department below that gave 120%. And I think it is an example of what a government in a country can do if they really want to, and especially a small, nimble government. And rules and regulations were drafted through select committees and went into law in record time. And we had unanimous support right across all of the parties in House for all of the laws. So, that comes with a little bit of work, but nevertheless, we were just very lucky to have, we built that kind of critical mass that both from a business perspective, from a community perspective, but also from a government perspective, that once you start the snowball down the hill, comes a point where you're just not stopping it. And that was, to build that snowball was a critical point.
Oh, that's fantastic. Well, I think it's it's pretty remarkable what you were able to accomplish and what the New Zealand government was able to accomplish as well. The other aspect I think that people often don't appreciate until they've gone through it is that if you're trying to build a rocket or build a company to build rockets, it's not just about the technology. It's about building an organization that can take on that challenge effectively. So tell us how you did that with Rocket Lab, and what are maybe some of the features of an effective rocket building organization that might be applicable for some of these students in how they run their own teams, or just in lessons for their future careers?
Yeah, I guess. Gosh, there's so many directions to go with that question. So I guess from a business perspective, let's purely look at it from a business perspective to start with. And I know this might not be that relevant, but I'm hoping that a bunch of the guys and girls watching and go out and build their own companies. But firstly, I see this more in any industry in the world where people have a cool technology, and then they find a potential market for that cool technology, but kind of blindlessly pursue the technology. And I think that's more prevalent in the space industry than any other industry. So as a result, especially unfortunately with this pandemic, you're going to see a lot of failure in this industry, because a lot of the business fundamentals are precisely not that. They're not fundamentals. They're something that someone's really passionate about, which is great, but remove a really buoyant funding environment and the thing just dies because nobody wants to buy it. So that, I think that's super important for a space company is, as emotional and passionate as you are about what you're building, at the end of the day, the business fundamentals need to stand on their own 2 feet super solidly. So, there's a lot of stuff out there that you kind of look at and you think, well, this is great, but how can that possibly work from a business standpoint? So I think that's certainly an important element. The other one, it's a little bit tricky. So I think just tenacity and energy are really the secrets in this business, because everything else, good engineering, tenacity, and energy are really, really the things that matter. So with the bilateral treaty, I just went and stayed in a Holiday Inn across the road from the State Department for 2 months, and I just told everybody, New Zealand Embassy, the State Department, I'm not going home. And I just turn up there 8 o'clock every morning. just not going home until we start to move. And the first couple of weeks, people think you're bluffing. By the time you get to the end of the month, you're still there. So you just cannot give up in this industry. And being very positive is important as well. So because you'll have plenty of setbacks along the way. I can think of it's a good example of this, and this is really defines Rocket Lab, if I'm honest. So before we started the Electron program, we were developing a new propulsion system, and we had developed this new propulsion system. My headphones are telling me the battery's low. If you stop hearing me talk, I'll just change to a different audio system. But actually, I'll do that now before it all turns to custard. Hang on.
Sounds good.
Can you hear me?
Yes.
Cool. So it was, so basically we built this new propulsion system. We had a whole team of guys turning up from America, and it's from a very large propulsion company that I'm sure you will know. And we thought we'd test this engine on the Friday night. They'd just got on the plane. We thought we'd test this engine just one last time. They were to arrive on a Saturday, and we tested the engine. And we had some bleed past a valve, and some propellant bled into the chamber. We had a hard start. And not only did we blow the engine up, we literally blew everything off the walls of the test cell. It was the biggest explosion in Rocket Lab history. Like, everything was just gone. And I remember, there was only sort of 5 of us in the team at that time, and we walked up to the engine test cell, and not a single person in there, was like, oh, we're screwed or anything. It's just everybody said, oh, well, I've got some titanium here and we'll get some stuff here. And we just started working. And, come Saturday morning, the team from America rang me up and said, hey, we arrived, we're feeling good. Let's start this engine testing. And we're like, no. You might get some jet lags coming on Monday. Meanwhile, we'd worked all through the weekend, and come Monday morning, we'd built a new engine. We'd got the engine test cell up and running again. But we did something that you probably wouldn't think was a good idea, is that while we're rebuilding the engine, we changed the design. This is one of those things where, sometimes it's good to take some bold risks. So we changed the design, and, the first time we lit that engine was in front of, a whole team of propulsion experts from a very large US propulsion company. And I'm glad we did, because actually glad we blew that engine up, because the new engine we built outperformed the old engine by about 15%. So it was super good. And the reason why I tell that story is because the easy thing to do there would be to go, oh, shit, we're hosed. And not just, focus on what needed to be done. And the safe thing to do would have been to build an engine exactly the same. But, sometimes you can't be safe, and you just can never, ever give up.
Right on. That actually gets at something that I'm also kind of curious about. And one of, I think, the fundamental paradoxes in aerospace engineering is that design is a very iterative process always. And it is always really important to make the right choices up front, because in the preliminary design phase, I think conventional wisdom is that usually about 80% of the cost and performance of a system are ultimately locked in coming out of that preliminary design. But the paradox is that that's the stage in a project where you also know the least. You haven't had the benefit of all the detailed design and analysis and testing that you'll have by the end of it. Once you're actually producing hardware, suddenly changes are a lot harder and more costly to make and have all kinds of system impacts. In a lot of traditional companies, part of how they tend to deal with that is by relying on very experienced, knowledgeable people who have been there, done that, and have built up sort of the intuition to make those smart choices up front. But what do you do if you're doing something that's outside of what you've done before? If you're a new team or you're doing something that's completely new, what can you do to try to help make those right choices up front to ensure that you're likely to have a viable product at the end of all of this, or at least avoid, costly redesigns and everything?
This is the secret, right? This is the secret, and it's not really a secret. So the challenge here is that there's kind of two approaches here. Is you can go one way, which is really, really experimental and just blow stuff up all the time.
Yeah.
Then you go to the other end of the spectrum, which is very analytical, and you can spend forever in analysis. And the secret here is there's an optimal point at the top of the curve here where you're doing both. And I think this is kind of probably the biggest success of Rocket Lab is staying on that optimal point, because doing experiments to understand fundamentals is super important. Doing the analysis to well enough, but only well enough to understand the results of the experimental is super important. If you go either side of that, it gets really dodgy. And we have a philosophy at Rocket Lab. It's called fail fast, but only fail fast early. Never fail fast late, because that's not failing fast anymore. That's just a giant pain in the ass. So generally we try and do all of the fundamental understanding down this end of the spectrum, so that when it comes to actually building the pieces of hardware, they really don't fail. Because that, as you say, that's a really expensive point.
Yeah.
And I think running a rocket company is it's like running through a maze at night, and in every dead end there's a guy with a shotgun. And you have to run through the maze sufficiently fast enough that you get to the end before you run out of energy. But also be cognizant of, when you come around that corner, you have to be careful and slow down that little bit and poke your head around to see if there is a guy there with a shotgun. Because basically, if you run into a dead end at such speed and you can't turn around, you're dead. Like, building a rocket company is like a million failure modes, and any one of them will kill the company at any point. Because if you make the wrong engineering decision, as you say, very early on, you can't iterate a vehicle or an engine, late in the piece. So it's knowing when to poke your head around the corner and see a guy with a shotgun and back out. So it's like going down an engineering path and realizing this is the wrong path, and then backing out. But not, it always looks greener too. So not going down a path and going, oh, we should go with this injector design, then back out and then into another path, and you never ever get to the end of the maze. So that's the secret, is being able to hold the course when you really think it's time to hold the course, but also when you're starting to violate the laws of physics, or things are getting incrementally harder and harder and harder and harder, knowing the point to just stop and back out.
Yeah.
But, this is the hardest thing, right? Is determining where all of that lies and making those decisions quickly.
Yeah. And I think that for the students, often this is one of the big advantages of say a student rocket team, because if you want to give yourself every opportunity to fail when the cost of failing is low, there's probably no easier way to do that than when you're a student, because your labor is free. You've got the resources of the university that you can take advantage of. You can get sponsored. Yep. So this is a great way to learn some of the things that will help you to be successful when you get into industry, so that you don't have to make those mistakes on a much more costly project. And I think that also ties into one of the things that we're really trying to focus on here with Launch Canada, and that is to put a big focus on technology development and encouraging students not just to launch rockets, but to think more about creative solutions to some of the real core challenges of rocket engineering. So what do you think some of those core technical challenges are that, say, students looking for some interesting and useful rocket-related projects might want to look into?
Yeah, so I think propulsion is not that hard. GNC actually is a pretty big element. So and GNC is often overlooked as something. If you guys is spun stabilized, passively stable rockets, then that's one thing. But when that was one of the areas for Rocket Lab that we invested in really early, and we actually we collaborated with Canterbury University and made a PhD course in advanced guidance, navigation, and control for rocketry. And we've had about 6 PhDs go through that course now, and we continue to support it. All of which have worked for us, and developed the core GNC algorithms for Electron and Photon. So GNC is a very, very tricky area. So I think that's an area that's often overlooked.
What about some of the the turbo machinery and propellant delivery aspect? Obviously, with your electric pumps, that's one of the major core technologies of Rutherford. How appropriate are things like pump projects for like really ambitious student groups, would you say?
Pumps are hard. But even electric pumps, on the outside of it, electric pumps look easy. And a low performance electric pump, it is easy. But a high performance electric pump is hard, really hard. The Rutherford pumps, the actual motors are smaller than a Coke can and produce around about 60 horsepower. So they're hard. But yeah, I would encourage anybody to do pump projects. I think they teach you an awful lot, and I would encourage universities, especially, to go after electric pumps, because a low performance electric pump is relatively simple, and much more simpler than any GG or other cycles. So I think, and for the scale of a rocket, it works. It's perfectly sized.
Okay. So now, I guess, getting on to some of the subjects that might also be of interest to the students looking ahead to their careers. What would you say is the most important thing when it comes to hiring junior engineers? Do you look more at a student's grades or degree, or do you look more at their hands-on experience?
Oh, hands-on experience, hands down. We look for two things: is what they've done, how busy they are in their personal lives, and really their who they are as a person. So we look for highly motivated people with lots of energy. They've done lots of things other than the university degree. At the end of the day, there's a whole bunch of people around the world get turned out of universities. They've all got the same degrees. It's almost nothing to distinguish anybody else out, apart from stuff that they build or stuff they do outside university. So the kind of people we look for are the people that use university to fuel their passion, rather than just go to university to get a degree and then we'll figure out, we'll go into the industry and whatever. Like we really look for hugely passionate people that have many more projects just outside the university projects.
Yeah. So sort of related to that, when you were initially setting up Rocket Lab and looking to find your initial employees, what were the traits that you were looking for in them, particularly at that very early stage when really the whole company is riding on a relatively small number of people?
Yeah, so disciplines and areas that we needed. But once again, attitude is everything. Attitude is absolutely everything. I will employ someone with half the grades and twice the attitude than the contrary. So looking for people who who are really super smart, can think outside the box, and just aren't afraid to work really hard. I think that was critical. In a startup, you can't carry any dead wood. You just, especially early startup, there's just no no ability to do that. So all the founding team of Rocket Lab still is still with us, and they are they're really the soul of the company that everybody is measured against.
Right. Yeah. With the cost of space access dropping, what do you think the new markets are going to be in the next, say, 20 years that will increasingly become legitimate business opportunities?
Yeah, I mean, I think there's a huge amount of opportunity in areas like weather. I'm very pro weather. I think it's an area that governments underinvest in, and it has a disproportionate outcome to all of us down here on Earth. So I think weather's going to be a really, really interesting, especially as climate change starts to people start to feel a few more effects from that. I can see that. Having a pretty good slate of sensors in orbit in a macro scale, monitoring the Earth in real time is probably a good thing to do. So I think that's an area that I'm really excited about. I'm less kind of inclined against the mega constellations. I think it's an interesting concept, and there's definitely some use cases where it makes sense, like broadband internet. But I'm less kind of enthused about some of the other mega constellations that are being proposed. I guess I'm more of the view of smaller number of spacecraft that are that are highly capable as fused in with terrestrial-based systems is probably a better way to go. But we'll see who's right or wrong about that one. But yeah, I think there's tremendous opportunity. I think we're in a time where there's tremendous opportunity for new systems and new approaches, and leveraging, as you say, leveraging the reduction in cost to orbit. This is the beginning of it.
With the moon increasingly being a major focus around the world, and here in Canada in particular, there's a new focus on lunar exploration, lunar technologies. What do you see the commercial prospects are for that whole aspect of space exploration?
I think it's going to be a bit longer to grow. I think the commercial opportunities really are government based. Until there's a commercial reason other than a government to go to the moon because we need some resource or something that the moon has, it's going to be a little bit longer, to see that develop really. And so I think that's really a government-led initiative. But the good news there is that governments are increasingly leveraging and relying upon commercial activity to service their needs. So look at us. We have the Capstone mission from NASA to deliver a spacecraft to cislunar orbit. And it's not long ago that would just never have been. That whole program just would have been an internal NASA program. It wouldn't have been the spacecraft that's been built by commercial entities and launched by commercial entities. So I think there's a lot of opportunity there.
Okay, so another of the questions that I know is upfront for a lot of students. Obviously, being in Canada with the United States right next door to us, ITAR kind of looms large over a lot of things that we do. And so this is why Canadians generally don't have an easy time if they want to, say, go and get their dream job at SpaceX. Rocket Lab, I think, has been really interesting because you're probably the first of the major launch vehicle companies that does fairly regularly employ Canadians out of New Zealand. But what do you think the future is going to look like for ITAR in particular? Obviously, you've been able to work through it. Do you imagine that there is likely to be some relaxation of that as the commercial space industry continues to expand internationally, or is this probably going to be there locking things down for the foreseeable future?
Well, I'm generally an optimistic guy, but I think ITAR's not going anywhere anytime soon. But it is you can navigate it. So, you know, we have a number of Canadian employees, as you mentioned, both in New Zealand and in our US. So, you know, half of the Photon satellite team is actually Canadians.
Oh, wow.
Excluding the Sinclair interplanetary guys. And we, as an aside, we really enjoy employing Canadians. They integrate incredibly well down in New Zealand. I'm not just saying that, it's true. I think the Canadian culture and the New Zealand culture is really similar in the fact that, you know, quite humble and respectful. And you know, that's very much, you know, the New Zealand culture. So we have a ton of Canadians down in New Zealand, and you know, they come in and integrate just seamlessly. So you know, I would say that's a great path for students, because we certainly, you know, we've had fantastic results. But look, ITAR is not going anywhere soon. In my opinion, it's a masterful piece of social engineering. I'd love to write a book about it one day. I think it's perfect in every sense, in the fact that you create sufficiently grey rules and put massively, you know, massively punitive, you know, penalties on it. Yep. So that it saves you writing like a description about every little possibility, because it just make it grey and then really nasty. So everybody will just never ever, everyone just is always just no. So as far as achieving what it needed to achieve, I think it was masterful. But it certainly doesn't help commerce, and it's been very damaging to commerce. But in saying that, you know, the State Department, we've found, doesn't want to say no. They're there to try and say yes and try and promote commerce. So look, it's not you know, it's not painless, but provided you go through the process and you very clearly articulate what you will do and what you won't do, we've found it, you know, the guys to be really, really reasonable. It is just a bit of a drag, that's all.
So speaking about you know, your increasing involvement with Canadians here, based on your recent acquisition of Sinclair, does Rocket Lab have any further ambitions of expanding in Canada that you can talk about?
Yeah, well, obviously, you know, the Sinclair team, you know, we really love the team, and you know, we love Canada, and we'll continue to increase the size of that team. Look, talent is really scarce all around the world. Really great talent is really scarce. So you know, we see, you know, Canada as a kind of almost an untapped market in some respects. Like I say, we've had really wonderful results down in New Zealand. So if we can continue to build the Sinclair team, you know, locally, then we'll absolutely do that.
Oh, that's fantastic. So is there anything you can tell us about some of the upcoming plans for Rocket Lab? I know some of the students are asking about Hypercurie, as well as some of your interplanetary missions. Yeah. Can you tell us anything about those?
Yeah, so, well, I mean, we should talk about the Photon in general. So, look, if anybody who looked at the kick stage when we first announced the kick stage, I would have thought it was going to be incredibly obvious that was a spacecraft, because, you know, it has a comm system, it has GPS, has laser and gyros, and it has propulsion, it has everything. But so it came as a surprise to me that it came as a surprise when we announced the Photon satellite platform based on the kick stage. You know, the plan was always to get into satellites. I think, you know, we see launch as relatively, you know, pretty much a solved problem. The next problem is that it's too costly and too time consuming to build a spacecraft. So, you know, that's the evolution. And it always annoyed me that most of the spacecraft that I was flying had all the same gear 6 inches away from the stuff that I had in my rocket doing the same thing. So it always just seemed crazy that we were, you know, it was just mass duplication. So that was kind of the point of the Photon platform. And Photon is not, don't think of Photon as a piece of hardware. Think of it as a concept. And the concept is a rocket is a satellite is a rocket. Electrons emit photons, so it's smaller. And we have a bunch of stuff that we can configure to basically build any photon we want. So we have like the kick stage based photon, which is a very good LEO platform. And then we have the Photon Lunar, which is a very, very high energy stage for doing lunar and interplanetary kind of stuff. But how all of that high energy lunar stuff came about was really, I hired a guy called Richard Hunter to do a PhD on what could you theoretically do with Electron in an upper stage and basically no constraints. And he did some really, really great work, did some orbital mechanic optimization and came up with some really cool orbits and really cool ways that you can phase orbits to go and do these things. So the Capstone mission to the moon that we're flying, there's a series of 8 separate burns on orbit. And we go into a very highly elliptical transfer orbit to start with. And over a period of sort of a couple of weeks, we raise the orbit through these series of burns into these highly elliptical orbits to the point that we, when we get right out to the TLI burn, we're way out there, and it takes very little energy to put us on a TLI trajectory. And it's a negative C3 initial trajectory. Then at that point, we separate off the spacecraft, they coast, and they get captured into the Moose gravitational field, and they do a series of maneuvers and carry on. We're also, officially our mission's over at that point, but we're going to carry on, but we're going to try and, basically I told the team we want a photo, really want a photo, a close-up photo of the moon, so let's do a lunar flyby. So we're going to stooge on out to about 3.2 million kilometers and then do a maneuver and then whip back round and then zoom past the moon in a low altitude flyby and try and get a picture. But the whole point of the PhD project wasn't to go to the moon, is I wanted to go to Venus. That was the whole point of the project. And I know that everybody's called for Mars, and Mars is, it's a great planet. But the reason why Mars has had so much, in my view, Mars has had so much love is because, it's the obvious planet for a human to go and put a footprint on. You can land on Mars and you can put a footprint on it. You walk around the surface, and it's great. Nobody's ever standing on Venus. It's just not going to happen. So it doesn't have that same capture of imagination about human spaceflight. But Venus though is incredibly an interesting planet. I think it's a great analog for potential climate change effects to the Earth. But the real attraction for Venus for me is there's 3 places in the solar system that has reasonable probability that life could exist. And one of those is in a sweet spot in the Venetian atmosphere, where it's around about 1 to 2 atmospheres of atmospheric pressures in the atmosphere. There's a relatively benign environment. It's still full of acid and nasty stuff, but there's hydrogen and oxygen. There's all sorts of stuff in that narrow band. And it's relatively agreed to that some extremophiles here on Earth could potentially live in that environment. So, well, I look at it as it's humanity's greatest treasure hunt to answer that question, and that's a huge motivator. So that's why I want to go to Venus. I want to go to Venus to search for life in the clouds.
Well, that's fantastic. I guess you don't quite share Elon's ambition to terraform the entire planet quite yet?
No. If you can terraform Mars, then Earth's got to be really messed up before you could Earth again. Like, if you've got to the point where the best option is to terraform Mars, and you have the capability to terraform Mars, fix Earth. Like, Mars is a shithole. Like, fix Earth. If you have that ability to God planets, do it to the one you're on.
I think that's a fair point. One other really good student question. You guys, I think, as some people might not realize, launched the first private rocket to pass the Kármán line in the Southern Hemisphere. What carried over from your experience with that project to your development of Electron?
Almost nothing from an engineering perspective. A lot of lessons from a regulatory perspective, because when we did that, nobody in New Zealand thought we were going to do that. And so there's a whole lot of things, we had to get waivers from the director of civil aviation, and we did it. And then everybody's like, holy crap. There was a whole lot of treaty stuff that just got messed up. And we, a day before the launch, we had New Zealand Customs ring up saying, hey, we're not sure you can launch because, space is not a customs destination. And technically you're going out of the atmosphere, which is out of New Zealand as a country, and then re-entering the atmosphere again and back into New Zealand. And we're trying to figure out what customs are going to do because we may need to inspect your rocket once it's returned. I'm like, dude, it's not coming back. So don't worry about it. But there was a huge, I guess I learned a huge amount with working with regulatory bodies, and really learned a lot about running programs, and I think I think I learned more about myself and more about other people than probably anything with that program.
Interesting. So with obviously with your Electron, one of your major focuses has been on additive manufacturing technology and some of the interesting things that's allowed you to do. Can you talk about just how important that has been in the development of Electron in Rutherford?
Oh, critical. Absolutely critical. I mean, if you think about injectors and pumps, if you had to investment cast pump impellers, and you just couldn't, you would have had to use platelets to get the kind of performance that we get out of a Rutherford. There's no subtractive manufacturing approach that would get the injector density and that we have in Rutherford. So absolutely critical. And we would, I remember when we were developing the pump, we would print 10 impellers, and liquid oxygen, turbo pumping is not, it's quite well documented to a point, but then it's just, and you just need to try. So having the ability to go out there and in one day run 10 different impellers, get 10 different pump maps, and then, a couple of days later go out with the Jesus impeller that has all your learnings in it, and away you go, was absolutely critical. It was, I think additive manufacturing was one of the biggest enablers for the program. If we hadn't had that, and that ability to just print engines, print injectors, print pumps, I don't think we could have done it.
Interesting. I think that's definitely something that is making a lot of more advanced, I think, rocket projects more accessible to a lot of students, because all of a sudden it does open up the possibility of things that would have just been way cost prohibitive otherwise. I guess the other major technology that Electron features, obviously, is your all composite propellant tanks. Can you tell us anything about how that development came about? Was that something that you'd sort of envisioned as one of the core technologies from the very beginning of the program?
No. So, but I have to say that my background is in composites. So, I was working for the government lab. It was advanced composite materials and structures, mainly supporting the America's Cup boats and some of the really highly loaded foiling and mass structures there. So I had a very deep background in composites. The original Electron, you'd be amazed to know, was made out of stainless steel. The original Electron was in stainless steel. But the reason why we went to composites, and I resisted the urge to go to composites because they were, nobody was building composite launch vehicles at that point. Composite cryogenic oxygen tank was still seemed as very researchy papery, and there was no examples out there that had flown, certainly, nonetheless, past full quals. So it was we started off in stainless steel, and really it came down to mass fraction at the end of the day, and it was I guess one of those things where I probably just should have started with composites from the beginning because that's what I knew, but we started off down the stainless steel road, but we just couldn't get the mass properties and performances to close. And you end up, in a small launch vehicle, mass is just so tough. It's just unbelievably tough. So, things that represent a negligible mass fraction on a big vehicle are significant on a small vehicle. Just a thing like a pressure transducer is all of a sudden it's an appreciable mass on a small launch vehicle versus a large launch vehicle. You still need a bunch of pressure transducers, and there's no miniaturized pressure. Pressure juicers don't scale with the size of rocket you build. So that was that was incredibly tough. So and once you build one thing out of composite, the best thing to do is composite metallic interfaces suck because you've got something with no thermal expansion against something with high thermal expansion. So you better to just make it all composite. And once you invest in the infrastructure to produce anything in composite, then everything else becomes easy. So as a result, the Electron launch vehicle tip to toe was all in carbon.
Wow. It seems like between the composites and the additive manufacturing, you've definitely given yourself a remarkably flexible and adaptable design. And I know that you've started looking into reusability. Can you tell us a little bit more about that and what sort of changes you think you might need to make to be able to enable that?
Yeah, so reusability is one that kind of snuck up and smacked me on the back of the head because from purely engineering perspective, if you look at the available or demonstrated solutions, they don't work for a small launch vehicle. So there was never ever going to be a propulsive landing on a small launch vehicle because now you're building a large launch vehicle and everything that goes with it. So it wasn't super obvious that was a feasible thing to ever do. And but it wasn't until we started getting some data back that we had a good understanding of the thermal environment, the aerodynamic environment, and it really the tipping point was when I was standing in front of the factory and looked out, and we were producing one rocket at that stage, sort of one rocket every 50 days. We're producing one rocket every 30 days now, and I thought, how can I double or quadruple production here? And the first stage represents 80% of all of the the parts of a rocket. So if you get it back, we didn't have to build much larger factories and a lot of other stuff. So it was really then started looking at data and realized it's crazy as I thought, and started down looking at different approaches. And there was some crazy ideas that we'd come up with, giant bouncy castles in the middle of the sea, drones, and nothing was off the table. But ultimately, we've ended up in a regime we think is really quite doable.
Okay. Interestingly, I mean, with launch vehicles, one of the big challenges for reusability has always been that the larger the vehicle is, typically, the lower the cost per kilogram of payload is going to end up being. And so I often find there are two schools of thought on that. One is that the way to go is ever larger rockets if you're trying to reduce costs, but obviously there are big advantages with dedicated launches as well. So can you comment on how competitive something like the Electron is with maybe say rideshare on a Falcon 9 and how you stack up?
Yeah, I mean, not competitive at all. What we say to people is, if you want to take a bus and you don't really care when you go, where you end up, you end up at a bus stop, probably sitting beside someone who stinks, take the bus. If you really care about where you want to go, when you want to get picked up, when you want to get dropped off, and you don't want to sit beside someone who's stinky, take an Uber. And they're two independent, separate markets. Yeah. So we never aspire to provide rideshare prices because we simply can't. It's a completely different service. So whether you're launching a Falcon 9 or you're launching an Electron, a lot of the costs are the same. There's a lot of fixed costs that are the same. Like flight safety doesn't change. It doesn't matter what you fly. Flight safety is the same. It takes the same size of flight safety team. The range is the same. Obviously it's a larger pieces of infrastructure, but the people you require to operate those pieces of infrastructure is the same. So there's kind of like a fixed level of cost no matter what rocket you build. That kind of puts a threshold on the price. But people who come and fly on Rocket Lab, they have to be a specific time in orbit and in a specific point in orbit. And we see a lot of customers who have built rideshare missions come to us. And you might go, well, that makes no sense because you can get a cheap ride on a Falcon 9 or on a Soyuz or something else. Why would they ever come to you? And they come to us because they've been delayed twice now, sometimes a year and a half. And the cost of being delayed, because you're still burning cash, the satellite's not making any revenue, or you can come to us and we give you real certainty over when you're going to launch. And, it's a pretty quick turn. So, most customers that come to us, we've launched them inside 12 months. So, it's a quick turn, and you have absolutely a certainty that spacecraft is going to be up there. And if depending on the spacecraft, if you count the lost revenue and sitting there waiting, delayed, or even if you're a startup company and you're just chewing cash while your satellite sits on the shelf, that's not sustainable either. So it really is a case where it's cheaper to get up on orbit faster on a more expensive rocket than it is to wait around for a rideshare. And then the other group of customers are customers that just absolutely need to go to a particular place. So things like LTAN and inclination are hugely important for a business of satellites. You can't just put a satellite up any old where. Great for like an experiment, but actually you need a spacecraft to be over a particular piece of landmass at a particular time. It may or may not need to be in the sunlight or in shadow. So there's real requirements, for companies to have those two things. So those are kind of the two kind of customers that we see. And generally, our rideshare customers have got their hair on fire because they fall into two banks as well. Within that is one, their mission's been delayed to the point now where they just can no longer tolerate it, or they don't fly a rideshare anymore. They just buy dedicated because they get schedule certainty, or they've been sold a ride on kind of like a developing rocket company that's continues to miss their milestones. They've been sold the dream, but never actually get there.
Yeah. So I've got a couple slightly technical questions from a few of the students, if you're able to answer some of these. I think a lot of people are really interested in your composites work, especially since many students will get into that when they're building, rocket body tubes and things. And obviously something like an all-composite cryogenic pressure vessel is sort of the ultimate. What were some of the challenges that you faced when you were trying to develop all composite liquid oxygen tanks?
Yeah, so there's two things you need to worry about there. The first one is microcracking. So interlaminar microcracking, because you'll be pressurizing with helium and you can't have a porous pressure vessel. So that's kind of the first one. And obviously cryogenics, depending on the resin system selected, really promote microcracking. So that's a challenge. Yeah. And then the second one is oxygen compatibility. And this is where you have to be really careful because you think about a composite pressure vessel under pressure. You've got a resin system with with laminate in it, and the laminate, especially when you're in your initial cryo phase, you'll hear tinging and ticking of the laminate as it breaks free of the matrix. But there can be a lot of energy stored in one of the the carbon filaments, and then as it goes through a thermal release and it goes crack, there's a lot of energy gets pushed into the resin around that filament. If that resin is in a pure and oxygen environment, fuel energy. It's not so. That having good sort of feed off each other, having really good understanding of resin systems, to control that micro cracking and that thermal expansion, but also resin systems that aren't hugely flammable. So where we ended up with, it was a big research program for us, where we ended up with, with our tanks are pretty much the same compatibility through BAM 4-hammer testing than that of, do you say aluminium or aluminum in Canada?
Usually aluminum.
Aluminum, yeah. So aluminum. So pretty much the same the same impact sensitivity as aluminum, which was a huge program. If you just take a normal resin system off the shelf, then I would be standing a long way away from it, for sure. Yeah.
So you developed an entirely new resin system in-house for this?
We work with people, yeah. We work with some people to solve that problem. Yeah.
Guessing you can't tell us much about how you approached that.
No.
So I noticed that some of the students seem to have gotten really interested in your comments about GNC and some of the challenges associated with that. Can you elaborate at all on some of the biggest problems that you encountered with GNC and how you went about solving them?
Yeah, I mean, so it's not so much the biggest problems, other than just GNC is really complex because, as you're flying a rocket, it's going through a continuing aerodynamic regime. The propellants are decreasing. The natural resonant frequency of the vehicle is changing. Then as you go through the atmosphere, you go through shear layers and the vehicle gets a big whack. Then, it's just continually changing. Like GNC for something that's very, well-defined and bounded is not a big deal, right? But GNC for something that is, by definition throughout the entire flight regime, nothing is ever constant, is where the challenges become. And you might build a good filter set to filter out bending, for the first half of the propellant drain, but then the next half is completely different because you're going way, way faster. You're going through different parts of the atmosphere and the vehicle's lost some stiffness. It's just, and damping. And then you have slosh. If you've got liquid propellant, you've got propellant sloshing around in there and you've got to reject that. And you've got to understand the difference between slosh and then bending modes. And then you've got your engines, and the engines are, all TVC, and you're coupling in all of this sort of stuff. Like it's just, I have tremendous respect for our GNC team, at Rocket Lab, because there's just so much going on. And then, at the end of the day, it's not just about, can we just get it there? It's getting it there really accurately. I mean, the GNC team currently, their record is plus 400 meters in insertion accuracy. So, it's probably 400 meters doesn't sound super accurate, but you have to remember that, you're traveling at 27 times the speed of sound at that point. And that's final insertion accuracy of 400 meters is mind blowing. After you think of all of the regimes, the stage separations and the closed loop guidance and all of the uncertainties there. So, it's not just about getting it there, it's about getting there exactly in the right place.
All right. Well, because I know that that you need to go, and you've been incredibly generous with your time, I guess one final question from the students to wrap this up that I think might be on a few people's minds is what opportunities are available at Rocket Lab for student internships, and do you have any advice to any students who are interested in pursuing that?
Yeah, I mean, we always look for internships. And generally within the local areas, we look for folks. So in New Zealand, generally we will look for New Zealand interns. Now that we have Sinclair and Interplanetary, then there's more opportunities in Canada. In saying that, though, there's a couple of interns we did very early on from Canadians that are quite major leads within the teams now. So it's not impossible to do that either. Obviously, the US is much more difficult for doing foreign national interns. But I would just say, if you're really really passionate about it, remember what I said, that sometimes no is not the right answer. So, you know, the HR team's going to hate me saying this, by the way, but you know, if you're really good and you're really passionate, sometimes no is the wrong answer.
Absolutely. Well, I think that's a pretty good advice to wrap things up on. So, Peter, thank you so much for very generously doing this for us. I think that was fantastic. And I'm just going to unmute all the students. Can we get a final big round of applause for Peter Beck?
Start with the competition.
Thank you.
Very good.
All right.
I love you.
You're the bestest.
All right. Thank you so much, Peter. Thanks again, and all the best to you.
Yeah, likewise, and all the best to everybody. And you know, keep building rockets. The best thing you can do is just do it. Just keep building stuff and launching stuff. It's the best thing you can do.
I think there's no danger of that stopping anytime soon.
Awesome.
Thanks again. Take care, everyone.
Cheers. Bye.
Thank you, Peter. Thank you, Adam.
Cheers.
Bye-bye.